I guess I should start by introducing myself. I don't have my employer listed on the front. I'm doing this in a personal capacity, but I work as a front office developer at JP Morgan in their commodities business, and we use Python pretty much 100% of our time to build all our risk management and trading applications. I've been using Python since 2000, so that's 16 years now, and have been using numpy since 2004 and Pandas for the last 3 years. So the goals for today's talk is to introduce the origins of Pandas as bringing together the best parts of Python, numpy, and R. And then we'll do some simple analysis based on sports statistics, but we'll go quite deeply into the typical operations that you'll do when you do any kind of analysis with Pandas. So that'll be looking at DataFrames, slicing rows from columns from DataFrames, how indexes work, and how the GroupBy works. It'll help you make sense of the syntax that Pandas uses, and it uses a lot of magic syntactic sugar so that operations that you think should work just like normal Python do, but with a lot more going on under the hood. And it'll give you a sense of what is fast and what is slow in Pandas. Often it's hard to know exactly what's going on, and that can make a difference in the speed of algorithms of 2-3 orders of magnitude, and similarly in the amount of memory you need. So this will help you develop a good intuition for how Pandas works, and it will really help you the most as you start to work on bigger and bigger problems with Pandas. In many ways, if you use Pandas just for very, very small data sets, efficiency and performance isn't really a concern because there's not much work to actually do. But it's as you scale it up that you really need to have a good understanding of what's going on. So to start with, we'll look at a comparison between ordinary Python and numpy. So with plain Python, let's say we create a reasonably sized object, in this case a list with 1,000 elements, and ask, well, how actually is that stored inside the Python interpreter? So, let's go back. So it's stored as a Python object. All Python objects are boxed objects, so there's a head to the object which says what's the type of the object and what's the reference count for how many names are pointing to it. There's some data that the object itself has, and in the case of a list, it has pointers to the individual elements in the list. In this case, these are integers, and each of these integers themselves is a Python object that is boxed, so that has the head that says I'm an integer and how many different objects are pointing to me. That lets the garbage collection, that's CPython. So that lets the garbage collection work. Now, PyPy, for instance, will optimize away that where it can. Similarly, Python, but that's the basics of normal CPython. Now, if we do a similar thing in numpy and create an array, this time we can specify the data type because we have much greater control over what's being used. In this case, I've chosen a 32-bit integers, and that looks very much the same, but it's actually stored in a far more economical way. So we have the simple boxed objects describing the essence of the numpy array, and then we have a long chunk of memory that's the actual data store. And we can see exactly how this plays out by checking the size of these objects. So the size of an empty list in Python is 64 bytes. The size of an integer is 24 bytes. This is in a 64-bit Python, so it's using 8-byte integers. So the total size of our list is 37K. So that's for 1,000 numbers. On the numpy side, it's the size of an empty array is 96 bytes. Each byte in this case, or each element in this case, is 4 bytes long. The total size of the array is 4 times 1,000, plus the 96 for the array structure at the start. And so that gives 4,096 bytes. So that's a far more economical representation of memory. It also means that from a performance point of view, for lots of operations on this data, we can do work in a far more streamlined way. For instance, one of the things we might want to do with a list of integers is to sum them. And if we do this in Python, this time on an array with 1 million elements, that takes 10 milliseconds. If we do that using the numpy sum function, then that's 1.2 milliseconds. So that's 10 times faster, and that gets its speed because the sum function in numpy is coded in C, and so it operates at the level of C, churning through the whole of that array. The Python one has to chase through all of these pointers to the objects, unbox them, pull out the integer value, and then add it up, then go to the next one and chase out the pointer and unbox it. So that's a lot more work. If we apply the standard Python function sum to our numpy array, then that actually takes 100 times longer, or 10 times more than doing it in pure Python. That's because before the Python sum function or list iterator can pull out the elements from the list, it needs to do the list lookup on the numpy side. The numpy will then box that integer, and then it will get sent to Python, and then Python will need to then unbox it to add it up. So this shows that even though from a syntactic point of view we're using functions that all are named the same, they can have very, very different performance characteristics. That was the one-dimensional case. If we now extend the data to the two-dimensional case, then it gets a lot more complex from the Python side. We have our list, which is then a list of pointers to other lists to all of the integers. That's one common way to create a two-dimensional array in Python. If we do the same in Pandas, if we do it in numpy, we can create just one single array. We can say reshape it, and we've ended up with an array of integers. Under the hood, these two arrays, they have distinct headers to each of them, but they're pointing to the same block of data in memory. So array number 2 here is a view onto the memory used by the first one. So we've created a new array, we've given it a different shape, but we haven't actually had to copy any data. We've just transformed a bit some of the structure in the header there. So that's a very, very quick operation. And that's something that Pandas exploits all the time to get its speed. And just to emphasize a bit how the slicing in numpy is working, we can do more tricks to, rather than just change its shape. We could, for instance, here say we want to start at the third element, go through to the end, stepping through every 3 elements. So we've now got a new numpy array, this red one. It points to data starting at the 3rd element in. And we can see that by calling numpy.info on our arrays, and that the first 2 have the same data pointers, and the 3rd one has a data pointer that's incremented by 12 bytes. That's 3 times 4. So this is pretty snazzy, and that's one of the reasons why numpy is really the standard way of doing numerical analysis in Python. In numpy as well, kind of showed how that indexing works. There are many more ways that we can do indexing. Take a scalar, take a slice. So those are standard things that you might see, that you do from with a Python array as well. But we can also pass in a set of row indexes, and numpy knows to pull out items from those points in the array. So we can pull them out. And there's a function called take that does that. And we can also do Boolean indexing, where if we have an array that's the same size with true and false values, and then we can pass that in to take a subset of an array, and we get the elements that correspond to where this was true. We can also carry that one step further, and when we're taking a slice like that, we can assign values to it. So if we assign -1 to this slice here, you see that we've ended up with -1 values scattered through there. So that's really nifty and really fast. So that's really the foundation of Pandas, and it was originally built as basically a thin layer on top of numpy that made numpy easy to use. So it's built on Python. Python gives us easy syntax, very easy to learn and easy to prototype with in a shell like IPython. Has a reputation for being slow. Another great thing that Python gives is a very helpful community that organises meetings like this, and that's really helped to get adoption. Numpy then improved on the slow reputation that Python had by introducing fast memory-efficient calculations and a whole lot of algorithms for processing that. And the SciPy project takes that many levels deeper, that now has everything from basic statistics through to machine learning algorithms. Very rich ecosystem, very powerful code, because it's all based on numpy routines that run basically at C speed, very efficient. Now, Pandas also brought along one more thing, and that is the concept of a data frame that borrowed from the statistics package R. Now, statisticians love R, and going back 12 years ago to the origins of numpy, R was used pretty much universally by statisticians, Python not so much. And the useful thing that R brought to it was an ability to label axes, put labels on rows, labels on columns, and add in new columns as you build up your data analysis. And that was something that numpy made, that was much harder in numpy, because you're dealing with fixed blocks of memory. You could take subsets of the memory, but it's less easy to expand it, and there's really no concept of labeling it other than through standard Python variables. Now, if we look at Pandas, it started in 2004 as a thin layer on top of numpy. with the basic classes of DataFrame, series, and a time series, origins, Wes McKinney in quant fund, and so time series analysis is very important. Index for being able to look up values from the data frame. And more recently, it's grown a whole lot more specialized types of classes for operating more efficiently. These are the classes you'll find if you do a import pandas and then look at what classes are in the top level pandas namespace. If you look in the code, you'll find that there are many layers of more abstruse objects. These are the ones block managers from a file called core.internals. And then if we look at a data frame itself, it has 425 methods on it. So that is great in one sense, because there's everything there that you could possibly want. It's not so great in another sense, is that often you don't know quite what you want and you're left trying half a dozen different things that sound superficially the same, especially around indexing. And then you go to Stack Overflow and do a search there and find that there are lots of helpful answers, and there are ones from 2010 that describe Pandas 0.8 that is very different from how these tricky problems get solved today. So it can be a little bit hard to move beyond the early things in Pandas to actually take full advantage of everything that there is here. So this means that Pandas presents a bit of a...
Quick question about these classes. If you look at the reference today, in 2018, you don't see many of these anymore. Is it because they've been eliminated?
I mean, there's a number of different things that the Pandas objects do. They have an ability to hide some of their methods so that they don't seem to be there if you're searching for them in IPython. And if you look at the size of the Pandas manual, if you download the latest version of Pandas, get the documentation as a PDF, I think it's 1,983 pages long. So there's a lot of stuff there, and a lot of it actually is not documented. Right. Yeah. So there's a lot there in Pandas, but it can be hard to figure a way through it. A lot of the syntax that you use to do things effectively is made easy for you, but that conceals what actually is going on under the hood. There are implicit conversions. So if it doesn't do exactly what you want, it can be hard to know how to make it do that. The code base is absolutely massive. So if you want to contribute to it, it's often you might take a look at it and think, oh yeah, I could add this function. And then you get lost in 18 levels of classes, and you're not quite sure exactly where to begin. And it's also changing rapidly. It can do a lot more. The expectations on it are growing all the time. And the more people that use it, the more applications they want to do. So a lot gets added, but also it tries very hard to remain backwards compatible. So a bit like an archaeologist, you can dig back through all of these methods in the data frame, and you can see which are the ones that had their origins in pure numpy, and then which have been added later on. And then you can see a more organized API emerging from that, but that can be hard to see from all of the detail. And the last aspect is that makes sort of bumpy learning curve is sort of big data. Everyone is trying to apply Pandas to bigger and bigger problems, and eventually you hit the stage where you run out of memory on a single machine, and you need to think about distributed solutions or more exotic ways of storing data on disk using compression, and then you end up having systems that have Pandas-like APIs, but they don't quite cover everything you want. So there's a lot of power, but it can be a little bit hard to make full use of it all. Okay, so that's a bit about the numpy background. That's the foundation that we need for starting to look inside Pandas. And we'll do that by following through the typical steps that you do in an analysis in Pandas with some relatively simple sample data. And the typical steps we do would be load the raw data into DataFrame, we'll do some formatting of the columns and add indexes so we can then start to really analyze subsets of it. Then we would aggregate it and subtotal it using things like GroupBy, and then we want to display our results. So these are the typical analytical steps. So let's follow that through for some sample data. And the sample data that we're going to use today is Aussie Rules football. Are there any Australians here? One down in the corner. So there'll be one person who knows what I'm talking about. Is it a bit familiar to you?
Yeah.
Yeah, okay. So one of the unusual aspects of Aussie Rules is that the scores are always given as a triple like this. And it's a very high scoring game, so scores of around 100 points are typical. You get 6 points for a goal, and you get 1 point for a behind, and the total is the points. In this data set, this comes from a website called AFL Tables, it's Australian Football League, and they have a list of the results of all football games since the original Victorian Football League started in 1897 in Melbourne, through to the latest games from last weekend. So this is a set of 14,840 40 games. And the two teams here are shown as the home team and away team, and then this R1 to R6, these are the rounds of a competition. There's a round robin competition, and then preliminary finals, semi-finals, and a grand final. If you haven't seen the game, it looks a bit like this. In fact, I'll play my short video clip, but you won't hear any noise. It's played on a massive field, so it can be up to 180 metres long. There are 18 players on a side, so there are so it's 36 players on the field. The referees run up and down the game, up and down the oval the whole time. So everyone runs a huge amount during a game. There's a lot of action. One of the characteristic things is taking a mark, which is this. You jump right up in the air and catch the ball. You catch the ball on the full, then you get a free kick. And the goals at the end of the field are like this. 4 sticks in the ground. Let me turn that. 4 sticks in the ground, 2 big ones in the middle. Those are mark the goals. In the middle is where you get 6 points if you get the ball through there. If you get the ball between the small goal posts and the big ones, that's a behind. And if the ball hits the post and goes in, then that's a behind as well. So that's what the game looks like. The end result, as you go through the season, is a ladder where they total up the number of games that are played, the wins, the losses, the draws, the total number of points for, and the total number of points against, and then calculate a percentage, and then rank the teams on the basis of points, 4 for a win, 2 for a draw, none for a loss, and then resolve ties with a percentage. So our analytical task for today is to go from that data starting point to that endpoint using Pandas, and along the way we'll dive into what's going on. We don't have a ton of time, so at various points I'll skip over some of the details. If you have more questions, then either ask at the end or ask me afterwards. And if you have the slides in front of you, then you can keep looking in detail at some of the things we might jump past. So the first step we need to do is to load the raw data into the DataFrame. Pandas has a ton of functions for importing data from every possible place and in every possible format. We use this read CSV function, which has a couple of nice things that you may not be aware of, where we can jump rows at the top, so that header we can take off, and if we specify the engine is Python, then we can use a regular expression for the separator, and we can cope with, here there's a dot and a single space, and between the other columns we have multiple spaces. So with one line of code, we can actually load everything into the Pandas DataFrame, and there it is. That's just like magic, and here's the end result. So if you imported using the sample code, this bit in green, to save you typing that in, you can just run that. If you've downloaded the data file bg3, then that will load that and import it into this DataFrame. If you aren't using Pandas 0.18, oh no, that's the next stage. This should work whatever Pandas version you're using, I think. So now let's look at the structure of a data frame. So if we, in IPython, if we just print out the data frame, we get something that looks like this. The bits in red, that's the index to the data frame, and in this case it's been added automatically, and it's something called a range index, which is a shortcut that rather than storing 0, 1, 2, 3 up to 14,000, it says I begin at 0, I end at 14,000, and if you want to look up a value, I can tell you where it is because I'm a smart range index. So that's how that works. The yellow bit is the columns. Now the column labels in a Pandas data frame is actually another type of index with the names of the columns, and it's an index because we want to, when we refer to a column, we need to look up where it is, and so that's using the index. If we get the D types of the data frame, now numpy has the concept of a data type. For the data that's stored in array, we had an int 32, and here we can get the D types, and this shows that the first column is a 8-byte integer. Then we have something that looks a little bit weird, less than M8NS, and that's a timestamp with a resolution of nanoseconds. Then we have all the rest are objects, and that's because they're strings, normal Python strings, and so they're stored as a reference to a Python object. If we do dot values on the data frame, we get back an array, or in this case, something called a rec array, because it's made of different types of objects, and this is what it looks like here. But that is stored as one single block of memory. There are no pointers to the individual elements within it, like there would be if we did that in Python. It's just the 8 bytes for the first one, 8 bytes for the timestamp, and then a 8-byte pointer to the Python object representing that first R1. So is it? In this case, normally in standard numpy, a rec array would store strings embedded within the array for a fixed length. Here they're stored as pointers, so you could change the pointer inside the array to a different Python object, and then it would look different in the array. Now, one of the things we want to do when we have a data frame like this is to select columns. There's the yellow index along column index along the top has the names, and we can pull those out. So let's compare how long it takes to get different chunks of the data array. The first one, if we do .values to get all of this data, that takes 35 milliseconds, which actually is quite a long amount of time, because Pandas hasn't actually stored that as one block, even though you might think so because a rec array has come out. It's stored it as individual arrays using something called a block manager, and then it has to stitch them together. And we'll see that in a moment.
Does that mean that in terms of memory management, if I have like 5 numpy arrays or a Pandas data frame, which might and goes through a loop that might change the size of it, it's pretty much the same performance? If it doesn't look for consecutive memory for 5.
It depends what you mean by changing the size of it. Sorry? Yes. So I'll summarize that.
Yeah.
If you've got multiple
Suppose
Pandas,
I have 5 numpy columns.
Yeah.
Suppose it goes through a loop that actually changes the size of these numpy arrays. Is that more memory or less memory efficient than putting it in a data frame, which will actually change the size of the data frame?
we'll see what happens as we change these data frames. That's some of the following slides. We'll get onto that. So let's just compare the relative magnitude of these numbers for a moment. We can pull out one series in 2 microseconds, which is pretty fast. And all that's doing is a lot like in the case of getting a slice from a numpy array. It's basically grabbing the memory reference to where that column is stored, and then sticking an index with that on the top, sticking a copy, or not even a copy, a reference to the row index on the side, and returning it as a Pandas series. If we do this last thing in a slightly different way and put double braces around it, that's what we would use to select several columns like we do here, and then we're having to build a new data frame, and that takes quite a bit more time. When I did this profiling, that was actually a really big surprise to me. I hadn't realized how much access to an individual series was optimized and how much more time it took grouping them together. Previously, I thought everything was more efficient if it was stacked together in a data frame, so I would take a bunch of individual series and want to put them together. And now that tells me, well, actually, getting an individual series is really, really quick, because when you know what's happening under the hood, it's just grabbing a reference to a numpy array. Behind the scenes, and the reason why this is particularly slow is we have a block manager, and a block manager actually takes care of splitting up the data frame into chunks that have homogeneous data types. So in the case of this data frame, we have an int block, a date time block, and an object block. And they have these different sets of columns. It doesn't matter to numpy that they come from different columns in the data frame, from non-contiguous columns, because they're all just references to the start of a different memory location. So if we're pulling out values from these data frames, that actually comes, is measured in nanoseconds, really, really fast via the block manager. And if we compare, if we've taken a series, the column home score out of the data frame, and if we compare it with the raw values from the underlying block and use is to compare object identity, see, they are referring to the same chunk of memory. So block managers are actually really neat because they make it really fast, but they're something that most people that use Pandas aren't aware of. So how many people here have you used Pandas quite a bit? How many people were aware of block managers? Okay, so one. So it's good to know that block managers are there because that's what's actually storing the data. There's also other things going on with a whole lot of caching, so that if we are accessing multiple objects multiple times, then we can bypass some of the lookups. Now, I've put this slide up not so much to go through the code, but to point out that if you're unsure what something is going to do in Pandas, or in IPython rather, put a double question mark after it and hit enter. Or if you're using a Jupyter Notebook, you could do the same thing. And that will display the docstring for that particular method, and then also the code. So you can see what actually is going on. So you say, well, I'm trying to look up an object on the data frame, look up a column by doing DataFrame square brackets on the column name. What actually is being called? And you can look at that and then trace through a few more levels of it, and then you get right down to the low-level guts of what's going on. You don't. That's kind of a shortcut way of profiling and tracing. You don't have to run anything, set breakpoints, but it's a good way of browsing quickly through the code. Now, if we are grabbing, say, a couple of columns from the data frame, to understand what's actually going on, when we're doing an operation like this, it actually occurs in two steps. The first step is internally it's getting an indexer for the columns, which, given the values we want, it returns integer indexes into the array, and then it does a take function which says, from slicing the array, which bits do I want, and that returns this thing in blue, which is a new data frame. The Pandas take function is more elaborate than the numpy take function, because the Pandas take function will stick back the columns along the top and the row index down the side, so that you get back the same type of Pandas object. So that makes your analysis easy. If we are selecting rows, then the numpy, same kind of numpy slicing mechanism comes into play again, where we are getting a view on top of the memory, and then the Pandas is putting back a row index and a column index. In this case, the row index that we want just a little bit of that row index. So that needs to get sliced up as well and then put back to give us a new data frame. But these are reasonably fast operations to do. If we look at the index on the blue data frame, you can see that it's still a range index, but it's now got a different start and a different stop. So under the hood in numpy, it's all got all kinds of clever ways to say what's the most efficient way to slice something. If it doesn't know how to slice it using some super efficient shortcut, then it will fall back to creating a full dense version of say that index, a full array with 14,000 elements, and then slice the bit out of that. So we can sort of summarize that selecting a section from a numpy table is doing a lookup in an index. It's then slicing a numpy array, slicing the row index for it, and then putting them back. There's some comparative timings there showing that the core operation here of slicing the data values is something that's very, very quick. So this is the first stage of playing around with the data frame. The next stage in our analysis that we do is we typically reformat some columns and then add some more elaborate indexes rather than the standard one. If you want to avoid typing in that code, you can run this in green from the sample code. Basically what we're doing is we want to split this into a section for the home teams and the away teams, so we can grab those. We first of all moving 3 columns down to an index. Then use this rather good string extract function with a new parameter for pandas 18 called expand equals true that lets us get out these 3 columns simultaneously, and it returns back a single data frame. So that'll give us a data frame with the scores, 3 columns for the home team and the away team. And here we're giving them with these named groups in the regex, giving it the names G, B, and F for goals, behinds, and then F is for the number of points for that team. And to get the number of points against that team, for the home team, it's the points against them is the points for the other team. And then we're doing two-step concatenation. Firstly, to stick the team name and the scores together to get a block for the home team and the away teams, and then stick those together vertically, or in this case using append, putting an index, putting team in the index because previously we had home and away teams separate, and then we sort everything so that everything looks nice and neat. And it's a sort of first step towards the ladder that we're trying to create. Does that make sense to everyone? It's fairly standard type of things that you do with numpy analysis.
Does it, when you show it, does it automatically group all the dates together like that?
So when you were doing index with multiple values like that, it's creating something called a multi-index. And so then when it displays the multi-index, it uses a sparse view for that. And just like a pivot table in Excel, it hides all the values that are repeated. They're actually there in the underlying data, but just for display it hides it. and there's an option where you can turn that back on if you prefer. So we'll just have a brief segue into indexes and how they're used to look up values. The idea of an index in Pandas is a little bit different from an index in maybe a SQL database. It's still used to look it up, to look things up, but an index is an object by itself, and it has a very specific purpose, which is to return integers saying where in an array you can find the matching values. And that's done with this getLock function, and it returns either a scalar or a slice, depending on whether the bits that you want back is from one element or a range of elements. If the index is monotonic, because then if you're getting a value back, it's always a slice. Whereas if the index is not monotonic, then if you want a value back, it may be disjoint, and then you get back a Boolean array. And these are things that we can put straight into users indexing for a numpy table to get back corresponding values very quickly. And that's what makes indexing fast. The other use of indexes in Pandas is for aligning labeled series and data frames. So if we set up two series here that have slightly different labels and then try to add them, you see that we've ended up with NaN values where one of them had a gap and the other one didn't. That's what's going on under the hood here, is that adding the two series says these series have different indexes, so it needs to form a union of the indexes to get a new index. It then needs to re-index the A and the B series, discovers that some of them have gaps, and it fills the gaps by default with a NaN, which is a float in the IEEE floating point NaN. So the whole of the series gets promoted from an integer to a float, and then we can add them together, and that gives us the result we see. If we wanted integers at the end, we would have needed to take care to align the indexes, filling the values with zeros, with an explicit 0, and then they would stay as integers and we could add them together. Now, in this particular case, we have 4 different levels of our index, and that's a multi-index. And the 3 key parts to a multi-index is we have the names, levels, and the values. So the multi-index is in red. The names here is the names up there. That's the labels that were attached to them. The levels say what are the unique values that are found in each of them. And then the labels here are integers that say to each one of these is the same length as the full list here. And so, for instance, for the venue, it starts number 7, venue number 7, 1, 2, 3, whatever that is. It's near the start of the alphabet, after Bellerive, so it's Brunswick Street. So that's how you look that up, and you can use sort of take functions to do that. Getting the values for this is really quick. This is 5 microseconds, and again, that's because this is a homogeneous numpy array. There's no block magic involved, so it's not like taking 35 milliseconds that we had in the example before. Now to select subsets of rows. This is one of the areas that can be most confusing with Pandas because there are many ways to do it. Now, one way we might do it is say we use GroupBy to, sorry, in this case what we want to say is for our ladder we want to take the 2016 games and we want to take the rounds that were the normal round robin and not the semi-final or grand final. So we want a selection logic like that. One way to do it might be to group by, iterate over the table, pick out the ones we want, and then concatenate them together. That takes nearly a second. Whereas if we do something like saying, looking in the index to see which rows correspond to the ones we want to keep, and then this will be a Boolean array, and then use that in the indexing with the scores, that takes 8 milliseconds. So that's more than 100 times quicker. So that shows that if you understand the numpy origins here, you can get solutions that are way, way quicker. Here there's so much machinery, numpy, involved in pulling out bits of indexes and data frames and sticking them together and so on, that it takes a lot of time. This is direct and super fast. There's a note here to say that there's actually a bug in Pandas 0.18 where this example doesn't work quite the same as that. Let's go over this. Okay. So one of the other things we want to do is we want to add some more columns. One of the things that numpy gives us is just like a dict in Python. We could say, let's create a new column for the games played, and for every row corresponds to a game, so we add one. In this case, we get this bizarre setting with copy warning that you might have seen and might not have really understood what's going on. But the reason is that this data frame here, through this slicing, Pandas has been smart and said, I can give you a view of some underlying of the original data without doing any copying. When you're trying to set something to it, it's then worried that you might be changing the original data without being aware of it. So it gives you a warning about that. And we can see that that there's a flag on this data frame that says that it's a copy of the original data frame that it was built from. So if we take a copy of it explicitly, where now this is copy flag is cleared, and we can set a new column on it without any warning at all. Now, if we insert a new column if we insert a new column, it's actually really, really fast. But that's because Pandas is smart enough to not do anything until it actually has to. So normally it would stick the new column inside the data block with other integer columns, but it doesn't want to do that more than it has to. So it will just accumulate individual data blocks until you try and do a calculation. Then when you do a calculation, it says, okay, now I need to put everything together, and you'll get a brief slowdown while it reassembles it into one block, and then it does that calculation. So now we've added the games played. Let's do the wins, draws, and losses. This example here shows various forms of syntax that numpy can use for doing that, that Pandas can use for doing that. Do you think that's going to give us what we expect? Not really, and that's because these, in this case, that was a Boolean, so we ended up with a Boolean column. So we should really force that to an integer. In this case, that D is a new column being created. It sets ones, but it leaves nans, puts nans where there's nothing else. So we can fill those nans with zeros, but that's left it as floats. So we can force those back to integers. Or alternatively, before we did that slice assignment, we could create a whole column of zeros, and then the slice assignment would update some of the zeros to ones, and it would all have stayed as integers. If we now look at the data blocks that we have from that, each operation has, each new column has created a new data block, and if we then do something that will force it to consolidate it, in this case explicitly call consolidate on the block manager, we end up with one nice tidy block again. The last thing we will try to do is subtotaling with GroupBy. And that's actually the syntax in many cases is really simple. It can get really complicated if you're resampling time series or doing custom groupers. But it's really simple. We can then add some extra columns at the end and then sort by those values rather than by the row index. And then just reduce the number of decimal places. And we've got the end result. So that's, we have actually achieved what we set out to do, which is pretty good. Just before we finish up, there's the code that did all that. We had an example before where GroupBy was pretty slow. If we took all the different chunks and concatenated it, it was 200 milliseconds. If we do it all in line like this, it takes just 4 milliseconds, so that's 50 times faster, which is pretty good. And the reason why is that inside, if we take this GroupBy, we could split it into two parts. So the first bit is actually getting a GroupBy object, and then applying this function to it at the end. And the GroupBy function is, it figures out what the groups are, and then for each group it has index offsets into the data array. And so if we then do the sum function on that, that's smart enough to look up these indexes and call that directly on the original data. It doesn't actually slice data frames, create new data frames to give them back to you. This sum function jumps back inside. So that's pretty nifty. So this is the end. The conclusions are that I think Pandas is pretty powerful. It can do a lot, and it can do more all the time, and often it can do that in a very few lines of code. The problem is that there are many, many different ways to achieve similar things, and many of them are not very good. And to help understand why some are better than others, it is really helpful to understand what's going on in the core of NumPy beneath it. To get this intuition for yourself, play around in IPython or a Jupyter notebook, and try scaling up to really big problems. If you do it with small data sets with 100 or 1,000 rows, everything will perform, kind of fast enough. Once you have hundreds of thousands, millions of rows, then it really gets interesting. Don't be scared to look inside the code. Use the double question mark thing at the end of a object or a method name inside IPython to quickly see what the code is doing. If you want to try some things at home, here are some ideas for how you could try putting some of the design principles from this talk into action in slightly bigger problems. So that's the end of the talk. Are there any questions? I think we have about 2 minutes left.
First on the slide 4, when you use scores.log, what does x is equal to 0 actually do? Because I wonder in the past.
Yeah. So that's.
No, sorry, slide with the title 4. so it's something like 33. Sorry.
Here, okay. So if we were doing slicing on a two-dimensional array, we'd need to put in x and y axes, or rows and columns. And in this case, this is saying axis 0, I want to do just the column. And then here, the column needs effectively a tuple with 4 slices within it. If we didn't put axis equals 0, we would need to make this a pandas, an index slice object, and then a comma, and then a colon to get all of the columns.
This is to understand, but we can't use lock on columns, for instance, can we?
You can, yes. This is just to remove. This is just to simplify the syntax.
No, but I mean only on columns.
No, lock is used for label-based lookups on rows or columns, either index.
Very quick one, because we are already out of time.
Sorry?
Do you contribute to Pandas?
I made one small contribution a year and a half ago, and then my work totally dominated my life. I always wanted to get back and contribute more, and so I thought preparing for this talk would give myself the understanding to come back and start contributing in a more substantial way, and hopefully it will help some of you guys get going as Pandas contributors too. Thanks.
All right.